Well, I'll start with his early career because there are a couple of outstanding institutions that are related to his life. High school number 57 in Moscow, Moscow State and Harvard University. Professor Pak is a specialist in combinatorics and probabilistic aspects of combinatorics. His expertise was recognized by various awards and invitations, such as to speak at the ICM in 2018. And he's currently a faculty member of UCLA, which has the oldest combinatorics group, or at least this is what it says on your webpage, that it was before combinatorics was defined as a field, and put it on. So please go ahead.
Thank you. This is very kind. And my high school is true. I don't know about the rest, but some of that. So I'll try to give. So first of all, thank you again for having me here. It's a pleasure to be back. I think I was here once time because did you, Francois, invite me? Probably somebody invited me, and it's great here. So I'm going to talk about what is a combinatorial interpretation, and but the talk is going to be nothing like any other talk I've given before. So it's going to have very little, almost no computer science, almost nothing like that. And I'll just try to give you some ideas of how I'm thinking about the subject and connection, and give some connection to polynomials.
What means
combinatorial? I just don't want to generalize and write. I figured you would know combinatorics as a word. So I'll start with semi-philosophical questions. What is the source of challenging problem in combinatorics for which we would need a combinatorial interpretation? So I have two, so this is part 0. So the first way to think of combinatorial interpretation is the following. Suppose you have an inequality A greater or equal to B. This is as general as it is. So suppose A counts some number of combinatorial objects, B counts some number of combinatorial objects, and what you would want is you want to find some kind of combinatorial interpretation for the difference A minus B. Right? So the second source of problems is, suppose you have some number P, which is a divisor of A, and then you want to find the combinatorial interpretation for the ratio A over P. So I'll give example. So I work. This is this is what I do most of the time. But I'll start with that because that's actually easier to understand, and the questions are very nice. And then I'll come back to inequalities, and I'll talk a lot about that. Everyone okay with this? And you should be able to interrupt me even if you're on Zoom and I'm not going to be able to see you. You should still ask me questions. Everyone okay with policy asking questions? Okay. So I'll start with the most I don't know if actually this is. I'll continue here. They can see. They can see. They can see. No, but the audience might not be able to see this part. So maybe they can see this part. So here is a very, very basic question. So we know that if you have if P is a prime, then P is and that P is going to be divisor A to the P minus A. This is called Fermat-Little theorem, and it's as well known as basically anything else in number theory. It's one of the most important results that we know. And so in this case, a natural question is what does a to the p minus a count? And that's the question is so simple I can actually tell you right away. Because it is do you know what it counts?
Words.
Yes.
Because you can
I'm not going to use the word words. Oh, I guess I did. Instead, I'm going to use necklaces. But yes. So what you can do is you can look at the necklaces where you can put I don't know what they call pearls, so that each of them can have a colors. Then the total number of arrangements of colors will be a to the p. Yeah. So of those, there are two types of those arrangements. Those which are monochromatic. So the whole necklace has the same color. There are a of them, and the remaining ones you can rotate. And because p is a prime, there is no period. So we can say that this number counts the number of a necklaces up to rotation. And that's as good answer as any answer that you can get in this setting. Okay. So it's actually perfect in many ways. So let's do another example. I'll just do one more. So there is a very famous congruence. 5 is a divisor of 5n minus 1. P of 5n minus 1. So this is one of Ramanujan congruences. What is P? I'll tell you in a second once I finish writing. So P of n is number of partitions of n. So now, once you write it that way, it would be natural, of course, to ask what is P of 5n minus 1? What does that count, right? And it's so natural that people have asked and people have answered. So let me tell you what the answer is. So this was the way I'm going to write it as a claim slash conjecture, which is proved now. So it was maybe slash theorem. So it was conjectured by Dyson in 44 and proved by Atkins, Swinert, and Dyer some years later that P of 5n minus 1 divided by 5 is equal to P0 of 5n minus 1 equal to P1 of 5n minus 1 equal to equal to P4 of 5n minus 1, where Pi of n is the number of partitions of n such that the first part minus the number of parts is equal to I mod 5.
Lambda 1 minus L.
L of lambda. So the picture that you might want to keep in your head is this one. So this is the first row, this is the first column. So you're subtracting, let's see if I have colors. So you're subtracting the first column from the first row and taking the difference modulo 5. And so this notion is called Dyson's rank. And by that, I mean, this notion is called Dyson rank. Let me write it somewhere. And if you look at the partition literature, there's a pile and pile of papers about this stuff. It's one of the most inspiring stories in partition theory. Now, there are problems with this. Let me now tell you the problem. The problem is everyone understood the claim, so it's now theorem. So I think it was published in 1955.
Is there something particular about 5 being there, or?
Yes. First of all, this is not true for like 13. But so 5 is the smallest one for which there exists a congruence. It's known that there are congruence for infinitely many primes, and it's a beginning of a giant story which I don't want to tell you. Partly because I don't know it, but partly because it will take me away from somewhere. Now here is an issue. The issue is that if I tell you this as a theorem, that's nice, but that's not what you want to hear. What you want to hear is why this equation is true. So what we did is we took all partitions and split it into 5 equal parts. Now, some things are obvious. So it's clear that P1 of n is equal to P4 of n, just because you can conjugate the partition. And same for P2 of n equal to P3 of n. But so we only have 2 more congruence, 2 more equalities to do combinatorially. We don't know how to do that. And that's very hard. And so somehow Dyson wanted to understand. So the way, I did speak to him once, and I think that's what he said. That basically he wanted to find a simple proof of that. And he thought that this would give a simple proof. And it doesn't. This Atkins-Winnerton-Dyer proof is much harder than the proof of the original congruence. Like this takes a couple of pages in Hardy Write as a good writing, or Hardy's lectures on Ramanujan. This one requires quite a bit more effort. So even though we do have a combinatorial interpretation, it's one of those combinatorial interpretations which doesn't actually explain anything about the original congruence. It makes it even harder, makes things harder. You see what I mean? But it is what it is. Just sort of telling you that combinatorial interpretation is not, even though originally it came from trying to understand the proof, just like in the Fermat-Little theorem. Here, there is no simple proof. Okay, I'll move on. Any questions about this before I move on? Final call? No. Okay. So now I want to go back to combinatorics and sort of part 3. This is my favorite example. It's the easiest example that one can possibly come up with, and choose n over 2 floor greater or equal, and then it's sort of falling down. So we have unimodality of binomial coefficients. Now, now we go back to the first line, and if you have unimodality, what you want to do is to say, okay, so n choose k minus n choose k minus 1 should be equal to something. Okay, and I'm assuming everyone in the room knows, but I'll write it anyway. So this is going to be the number of, let's say, 0, 1 sequences with k ones, n minus k zeros, such that number of zeros greater than number of ones in each prefix. In other words, this is really a solution to the Bellet problem. Okay, so that's just because it's a number of solutions, that means you should think about it that way. You can think about it as combinatorial interpretation for this inequality. Okay, so I'm sort of thinking in that direction. Is that clear? Everyone good with that? So I'm assuming you've seen this before. So now now the next part is going to be something that is just as famous, but you may not have seen this before. So here is, so the next part is going to be a really celebrated theorem by Hellman and Lieb. This is 1970. It's I'll write the inequality, and then I'll explain what I mean by that. So it says that some sequence of numbers is log concave, where mk of g is the number of k matchings in G. So k matching means so G is a graph. So G is a graph, and we're looking at k matchings in G. So those are k tuples of edges with disjoint vertices. Okay. So typically, if this is a graph, then those will look that way. Is the statement clear?
The K is the number of matching.
What is K matching? I don't understand.
Okay, it's so we have K K edges, K disjoint edges. It's not a perfect matching. It's so those are K tuples of edges with all disjoint vertices. Everyone? Okay, good. Now you know what I'm gonna do next. So you see, this inequality was not proved combinatorially at all. Original proof used essentially linear algebra, eigenvalues and stuff. So what you can ask is, suppose you have mk squared, mk minus 1, mk plus 1. Is that equal to something? Is there a combinatorial interpretation for that? You think yes? No?
I think yes, because we talked about it.
Just wait. I'll talk about some both positive and negative stuff, but yes, you're correct in psychology, and so it is true that this has a combinatorial interpretation. So this has a combinatorial interpretation, and that's because we have a proof due to Kratenhaller. I think this is 94, and I'll give a sketch of the proof just so you can see the flavor. You will, once I tell you the flavor, you can reconstruct the whole proof. It's not super hard. Okay, so you ready for the proof? It's the only kind of non-trivial proof I'm going to give, or hint of anything at all. So the way it works is the following. You start here. You have what does that count? Or equivalently, you start here. You have k minus 1 matching and k plus 1 matching. So you want to put them. You want to put one on top of another. So let's choose something. So that's one thing, and so 4, 5, 6, 7. So, and we also have some 5 edges, which we put somehow 1, 2, 3, 4, 5. Or actually, why don't we do it a little differently? We put it like a separate edge. Okay, so that's what we did. Now, what did we get? So what kind of well, in this particular case, we have so when we overlap 2 matchings. So we overlap m and 1. That's k plus 1 matching, and 2. That's k minus 1 matching. And when you take a union of m+1 and m+2, which can have the same edges, I just visually drew them differently. So that's going to consist of, so there are several cases. First case, there could be cycles. We're going to just ignore them. But you see where I'm going. I'm going to start with, so it's going to union of, I'm going to start with 2 matchings, and I'm going to create 2 other matching, 2K matchings. Okay. So if there are going to be cycles, I'm going to ignore them. What you can do is, what you can have also paths. Some paths are going to be balanced paths, equal number of blue and orange in this case. Okay. So balanced paths. I'm also going to ignore that. I'm just going to leave them untouched. Okay. And then there are going to be unbalanced paths. So for you can see a whole bunch of them here. There are those which have blue majority, and there are those which have orange majority. Okay, there is going to be 2 more of those than this. So there's going to be L+1 and L-1 of those for some L. Okay. Now there's something you can do with so those are unbalanced paths. There is something you can do with unbalanced paths, and specifically you can just take the whole path and recolor. You recolor every blue with orange and every orange with blue. Okay. So there are 2 to the 2L ways to color this. Yeah, in principle. So in order to keep the same number of blue edges and the same number of orange edges, the total number of ways to do that is going to be 2L choose L+1. I think that's clear. Yeah. And there's going to be 2L choose L ways to color them so that they have that you get 1 less blue and 1 more orange. And
-1?
no, this is L, and this is L+1, and this is L. Yeah. So those are not in. Those cannot be obtained as a union of 2 those matchings, but those can be obtained as a union of 2 K matchings. And now from the previous remarkable theorem, we know that. And the difference is a Catalan number, but that's completely unimportant for this discussion. The point is we have a combinatorial interpretation and we have a combinatorial proof to do that. That's because we have a combinatorial way of actually, well, you know, the reflection principle. We have a combinatorial way to prove this result. So we can construct it in a so if you take those 2. You can construct an injection and create M1 prime union M2 prime, 2 matchings, which are both K matchings. Let me leave the details away. But that is Kratman-Hadder's proof. You see what I mean? Now, what it did is it proves the Hellman-Lipp theorem. But if you now walk through that proof, you can realize that, oh yeah, there's a couple of number of ways to do that, and then you can give a completely combinatorial interpretation for the difference. Okay, let me not do that as well. But you see what I mean? Once you this is an example of the result that once you find a smart proof, you do find a combinatorial interpretation. Can I move on? Okay, so now I want to move to what I actually do. But before I do that, I have a tiny amount of space here. Hello. So let me state the theorem. This is, I'll abbreviate adipracito Foucault's, and this is 20, I think. So suppose Fk of G is a number of K forests in G. Okay, so that's a K tuples of edges which don't form a cycle, which don't have a cycle. Everyone clear with this? So what they proved is that Fk of G square in a similar way greater or equal as K minus 1 of G times Fk plus 1 of G. So we have the same type of log concavity. And now here is a really interesting question. Does, in the same sense, we have a combinatorial interpretation of that? Is that a combinatorial interpretation? I don't know. So the reason I don't know is because the proof of that is difficult. The original proof is heavily algebraic, and it definitely cannot be turned into combinatorial proof with Swee-Hong Chan. Let me write his name. Swee-Hong. So Swee-Hong Chan and myself, we wrote a very long paper called Combinatorial Atlas, where we found a simple proof. Simple meaning not many tens of pages, but few tens of pages. So you need sort of a setup, maybe like, so essentially on 15 pages we can prove it from scratch using this. But it's still our proof uses nothing but linear algebra, but still rather technical. So the answer is no. We don't have a combinatorial. We don't know whether exists a combinatorial interpretation or not. And I'm really interested in this problem.
So if you think about this as these numbers as being like entries of a matrix along diagonals, this is a 2 by 2 determinant.
Correct.
The 3 by 3 determinant is also the same property. 5 or 2, whatever.
That's a good question, and I'm not an expert, and I think the answer is yes. But in some cases, I don't know if it's in this case, but this are called people looked at that, yes. And in fact, 2 by 2 is exactly the right place to start to look at that, because essentially at the end of the day, we're proving that some matrices have one positive eigenvalue, and from there. This follows. So you guessed right at the beginning, but for 3 by 3 it's more complicated. So where are my notes? Okay. So now I want to tell you a little bit about polynomials, and depending how much time I have, I'll tell you more and more. So essentially, the talk can start from scratch. We're not, well, I'll come back to some of the questions in the talk, but people obviously looked at, so I tried to look who was the first to figure that out. Do you know which century? Can you guess which century? I have only the upper bound. I don't know if the upper bound is tight. No. This is so the reference I found is 13th century, but they didn't have a notion of proof. They just observed that in some 13th, no 13 in rabbinical integer.
Yes, okay.
Yeah, so they were like, oh, there is something. But Euler is definitely not right, because it very famously follows from Newton. So and this would be our introduction to polynomials. So Newton looked at elementary symmetric polynomials, and he proved that I'll write the same inequality twice. He proved the log concavity, and so he proved that inequality for all over reals.
These are elementaries.
Elementary symmetric polynomials. Oh, I should have written that.
This is what you would.
Finite. What?
Finite, maybe not.
Yes. So it's k of x1 up to xn is defined as summation over all 1 less or equal to I1 dot less or equal to actually strictly less ik less or equal to n x1 dot x right xi1 dot xik. You see, I'm not prepared for it. Yeah. Everyone okay with this? Now, of course, that's not what he really proved. He really proved a stronger result. So this implies unimodality of binomial coefficient. You just put ones. So the real inequalities that he proved are ek over n choose k. So this sequence is log concave. Let me not write that. So that's a stronger result. So if you quotient by binomial coefficient, and when you apply to this becomes even obvious because you divide binomial coefficients by themselves and you get ones. But of course this is a much stronger result. So this is log concave. But this, but once you think about it, it lets you it lets you to the following question: what do we want polynomials to satisfy? So suppose you have two polynomial. So when do we want to write f greater or equal to g? There are, let's say, sort of a classical way or analytic way to do that. If one polynomial is greater or equal to another polynomial for all values of variables, let's say non-negative values to make it easier. So for all xi's in R plus, actually R plus is probably better. But that's not the only way to do that. Another way to do that would be to say that f minus g is in n of xi. So if you get a positive sum of monomials, non-negative sum of monomials, you see what I mean? That's a much stronger notion. So we would write. I would keep this notion, but over monomials, I would write that notion. So it turns out that from computer science point of view, there is and of course for symmetric polynomials you can write sure positive and e positive and so forth, and people do that. Let me not talk about that, but there are people in the room who are experts on that and who can tell you more than I can. So there is for classes of polynomials there is more to the story, and what I want to do is I want to write an intermediate notion f greater or g. I'm going to put a hashtag below. Indicates that the difference has a combinatorial interpretation, whatever that means. And I'll explain. I'll explain what I mean, and I'll explain it in one example. I wrote rather long, rather long example. So example, 1/5 of x to the 5 minus x. So that's a polynomial. You see? So that turns out to be equal to 24 x choose 5 plus 48 x choose 4 plus 30 x choose 3 plus whatever 6 x choose 2. That's just an identity. Okay, but now that identity tells you something. So we want a combinatorial interpretation of that. You would think that we already know it. Oh, number of necklaces. But that's not how I want to think about it. I want to say that, well, suppose X is not some abstract number. Suppose X counts number of Hamiltonian cycles in graph G, or three colors, or anything like that. So for those of you who know a little more, so I want to think that X is a sharp P function. So it counts, suppose X counts something. But you're not going to lose anything if you just pretend that it counts Hamiltonian cycles in graph. Okay. Now, what does this number count? This number counts, 24 times something. What does X choose 5 count? That counts 5 tuples of Hamiltonian cycles in G, which are all distinct. That's very easy. You see what I mean? So therefore, this number has a combinatorial interpretation because it's equal to sum of combinatorial interpretations.
But do you have a natural way of integrating 24, 48, 30, and 6?
Well, this is 5 tuples, and 24 is a number. 24 is a number that you can just put a label at it. One of the flavors.
I want more.
Okay.
I want a combinatorial mixture of the two that says that 24 counts something that's meaningful, links to X5, and 48 is something meaningful of the same kind.
Okay, so of course, if you look at the necklaces, that's where it comes from. I'm trying to make a point that I would think that this is, you don't need to know about necklaces. This is good enough. Perfect is enemy of the good and all that. But it's true that it comes from necklaces. If you start looking at necklaces, then you can figure it out exactly how to do this, how to get this coefficient. And so now our main theorem is that there is nothing else, in a sense that.
I have another question, sorry, but
Okay.
because of the little Fermat theorem, it implied the little Fermat theorem for the prime 5. Have you always such an identity?
Yeah.
For any prime or?
It also follows from necklaces, but yes, for every prime.
And so these numbers, 24,
And they're all going to be
have
positive.
some meaning, or?
Yeah, just that's what I was trying to answer Francois, who is smirking, and now pretending not to smirk. They do count some number of types of necklaces with different distributions of colors. So those would be all colors are different, and 24 is 4 factorial, and you can figure out the rest. The point I'm making is that we want to define what. We want to define what do I mean by the difference of polynomial having combinatorial interpretation, and the right definition slash really complicated theorem says basically that f greater or equal, so there is a combinatorial interpretation for that if and only if f minus g is in n of sort of product of xi, choose well, some kind of ki. So if it's a product of following binomial coefficients. Each of for each xi, there is a kind of obvious oblivious combinatorial interpretation, whether they count Hamiltonian cycles or recurrence or whatever. And I'm saying that there is nothing else. And to explain, so this is a definition. So we want positive. So everything has to be positive here. To explain why this is a theorem, it would take me way too long time. But essentially, if you under some various complex complexity theoretic assumption. If you think this is generic, sort of general sharp P functions, we're going to look at polynomials which preserve the resulting function to be in sharp P. Okay, and that would be a characterization. So of course, you need to understand that every integral valued polynomial is in Z of those. That's a 100-year-old theorem. And we're saying that that there is a combinatorial interpretation if and only if for the difference, if the difference is positive in the product of falling the factorials. Now, the remaining time, I don't know how much you're the boss. How much time I have?
15 minutes.
15. Okay, great. That's what I wanted to hear. So I'll tell you some results and applications. So let me tell you what Kretenhaller's proof. So what Kretenhaller's proof implies that mk square minus mk plus 1 mk minus 1. Let me be careful. I'm going to define, I need a mu k to be sum over all perfect matchings. Pi is a perfect match, sorry, not perfect matching, k matching. K matching x to the pi, x to the pi, where x to the pi is defined as a product over all edges in pi xe. So I'm going to define a monomial for every matching. So that gives me a polynomial mu. And all variables correspond to edges of the graph. Okay, and now this proof, Kretenhaller's proof, tells you that mu k square is greater or equal than mu k minus 1 times mu k plus 1. Where this is greater or equal, it follows from Hellman and Lieb that this greater or equal is this greater or equal. But his proof shows that you can get a monomial inequality, and that doesn't follow at all from Hellman and Lieb. That's a new theorem that Kretenhaller never noticed he proved. But you see what I mean? And the curious thing is, if you write the same story for the Prasida Hukas, you still get for the corresponding polynomials, not write that, but you would write x to the power of the forest. Okay, in exactly the same meaning. Then you would get then you would let me use capital F's now to correspond to polynomials fk. So you would get fk minus 1, fk plus 1. So you would get that for all values of x, negative values of x. But and it's an open problem whether this x is actually true over monomials. We don't know. I actually kind of conjecture that, but conjecture is weak because we tested it on relatively small size graphs. So whoever can do beyond 7 vertices has an advantage over us. Okay? Because that, if it's not true, it's even more interesting. Then one can ask about combinatorial interpretation in the definition that we defined here. We don't know. We don't know at all what's going to happen. That's way too complicated as an inequality.
For like spanning, if you do something similar for like spanning.
There's no k.
Without k, you need.
What's a k? So there is a spanning tree inequality, different one when you have a number of spanning trees that's due to standard that has k edges in some subset, and I can say a lot about that, but let me not do that right now. So what I want to do is mention a few inequalities that for which the answer is negative, and the first one is going to be really easy. So if you take x minus y squared, which that's x squared minus 2xy plus y squared. Now that one, that one. Okay. So let me now say what I mean. So that this is not greater than 0, according to my definition, and you can sort of understand why. So you can of course write that in terms of this basis, and you're going to get some negative terms. But you can also understand why. It's because if it did have a combinatorial interpretation, then you can think of x as number of Hamiltonian cycles in graph G. You can think of the y as number of Hamiltonian cycles in graph H, and then you would have access. You would be able to tell if two graphs have equal number of Hamiltonian cycles, and that's a bad sign for anything. You should not have a machine which does that. In this framework, it would be CoNP, but let me not do complexity theory. This is just a bad sign. Okay, so to be more precise, if having a combinatorial interpretation for this number would give you an evidence that those two numbers are distinct.
So the numbers look the same. What did you write for the second one?
H. So if you had a combinatorial interpretation for this number, then you would have a witness for these two numbers being distinct, and you should not have a witness. That's how computer science tells. That's what computer science tells you. So there shouldn't be a polynomial time or combinatorial objects that you can test that they exist, which will tell you, oh no, those two graphs for which you know nothing about, which is very hard to compute number of Hamiltonian cycles, have a distinct number of Hamiltonian cycles. That would be weird. This is sort of a motivating example for the whole thing. And but now you can look at in the remaining few minutes, I'll tell you just a couple of inequalities that you can do. So for which you can study, and I think I'll give you one easy and one very hard, just so that you can see how that works. So if you look up standard analysis books on inequalities, so here is one. I think I lost count, but this is called Cauchy's inequality, and it's a really basic inequality which looks like this: x, y, yi, I from 1 up to n squared less or equal than sum of x I from 1 up to n. Xi should be squared times sum of yi squared, and from 1 to n. Do you see why it's true?
There is a power.
There is no square. Yeah. Now you see it's true. Yeah, it's a scalar product. Scalar product of two vectors. So the length of the scalar product versus the length of the vector. Okay. So let's call it a proposition. Proposition. I'll write it this way. Cauchy is Cauchy inequality does not have a combinatorial interpretation. So now let's parse that. We take the right-hand side, subtract the left-hand side. That's a polynomial. You write it in this basis, you're going to get negative terms. That's what we're saying. And it suffices to do it for relatively small n. I think n equal to n equal to 2 is good enough. And that's because for n equal to 2, you already run into this obstacle.